Hi, good morning, good afternoon, good evening. This is Jimo coming to you again. Whatever the case may be, I don't know which part of the world you are, so just take it. Today I'm coming with binary operations. Binary operation is one of the topic that is seldomly taken in our coaching centers, especially if you are not a further mathematics student. So this is what I'm bringing to you today. Before we go, I just want to take you through some definitions of terms. You need to know this one. And the first one is the binary operation itself. What is binary operation? Binary operation is an operation which combines two or more pairs of numbers to give a single element or a number. Let me take an example. You all know it. For example, 2 times 5 is equals to what? What? 10. Good. This is an example of binary operation. For this reason, I say example of binary operation is addition, represented by cross or plus, subtraction, represented by hyphen, division, represented by this, I don't know what to call it, multiplication, asterisk or stars, this form, etc. You have multiple of this example. So this is a basic definition in binary operation. You need to know what is binary operation. Whenever you are given any question, all this will be defined for you, as we're going to see later. Now, another very important definition is closure. What is closure? If I say it, what is the meaning? So let's go this way. We say a set as closure under an operation if performance of that operation on members of the sets always produces a member of the same set. Don't be afraid, okay? This is just English. Let me give you an example. Just very simple one. For example, if I have a set of numbers R and I have defined members of those sets as 1, 2, 3, 4, 5, and 6. Okay, this is the set, the members of the set R. Okay, if I have an operation plus and I say 1 plus 3, 1 is a member of this set, 3 is a member of this set, and it gives me 4. Look at it. 4 is also a member of this set. So since 4 is a member of R, therefore I can say plus is closed in R. Okay, another example. If I have 2 times 3 is equals to 6. 6 is a member of the set. This is 6 here. So since 2, 3, and 6 are all member of set R, then I will say multiplication, which is times, is closed in R. So since 6 is a member of R, then multiplication is closed in R. As simple as that. I do believe you understand. Another definition, identity. Identity. In English, when you say identity, identity means something that is unique, is just different. In the language of mathematics, it means a number or an element which, when operates on another element, it leaves that element unchanged. In mathematics, identity means it means a number or an element which, when made to operate on another element, it leaves the element unchanged. For example, if I have 0 plus a, it is the same as a plus 0, and it is a. For this reason, I will say 0 is an identity element. For a general definition, which we are going to be coming across, I will say I star m is equals to m star I and is equals to m. Then, so for a general definition, we say if I star m is equals to m star I and is equals to m, then I is an identity element. This is all about the third definition. The fourth one is inverse. Inverse. You know, it's just the reverse of something, but in mathematics it's a bit different. It's not just as straightforward. So inverse, given an element A in a set. If there exists another element A inverse such that A times A inverse is equals to I. Remember, I have used I as identity element, so I will define it. I will say where I is an identity element, I is an identity element, then we say A inverse is the inverse, make it clear, inverse of A, or it can also be vice versa. I hope this definition is clear. We shall take some examples, so just bear with me for now. Okay, so if you allow A to operate on A raised to power minus 1, and at the end what you get is the identity elements, then you can say A is the inverse of A raised to power minus 1, or A raised to power minus 1 is the inverse of A. Please note, I need to add this one. Notes, some elements have no inverse. Just take note of that. Though for JAM students, your question will always be straightforward, so no cause for alarm. All right. Now, let me take a fresh page for number 5. This is a definition, and it is as well as laws of binary operation. So let me just write somewhere here and say law of binary operations, but I will call it definition of terms number 5. So the first law we're going to be looking at is commutative law. If A and B are members of a given set, and A star B is equals to B star A, then we say the operation star is commutative. We say the operation star or asterisk is commutative. let's take an example. Just I'm gonna give you that example that you know. If, for example, e.g., you all know that 2 plus 3 is 5. And what about 3 plus 5? I mean 3 plus 2. 3 plus 2 is also what? It's 5. Therefore, we say plus is commutative. We're gonna say plus is commutative. What about this? 3 minus 2 is equals to 1. What about 2 minus 3? It's impossible, right? It's impossible, right? It's possible. Oh, it's possible. You know, in my primary school, we used to say it's impossible. So it's possible. It is minus 1, right? So since by interchanging 2 and 3, we got different answer, then we say this operation minus is not commutative. So it is not commutative. Definition of terms 6. Associative law. Given that A, B, and C, A, B, and C are members of a given set, right? So if A times B into C is equals to A into B times C, right? Then asterisk, this star operation is associative. You can see A and B are friends here. C is standing alone. But when you come here, A is standing alone, B has left A and went to meet C. So B associates with A here, and here B is associating with C. Then we say such operation is associative. Let me take an example. If you have 2 times 4 times 3, what do you get here? This is gonna be 8 times 3, which is 24. Then let me see if I have 2 times 4 times 3. It's going to be 4 times 3 is 12, so still 24. So for that reason, we say this operation is associative, right? The operation is associative. Number 7, distributive lower. Given that A, B, and C are members of a given set, right? And these two operations, dot and stir, are binary operations. Okay, if A dot B star C is the same as A dot B star A dot C, then this operation dots is distributive over operation stir. For example, let's just bring very simple one. If you have 2 dots 5 plus 3, and this dot was defined as a multiplication. So from our primary school mathematics, we know that we're gonna open this bracket, okay, and for that reason we're gonna have 2 that's 5 plus 2 that's 3, and this will be 10 plus 6, and this will be 16. So for that reason, okay, before the conclusion, you see, if you do it this way, you're gonna get the same thing as if you say 2 dots 3 plus 5 is what? Is 18. I mean, it's 8. So I'm gonna have 2 that's 8, and this is gonna give me 16. You can see the answers are the same. So for that reason, you can conclude that this operation dot is distributive over what? Over plus. The operation dot is distributive over plus. Thank you. The battery has stayed for long. So these are the basic definitions, and I must tell you here as an information that from my experience of studying so many JAM questions have not been coming under distributive and associative. You only have questions under commutative, inverse, identity, and so on. So hardly will you get question under distributive and commutative. We're going to solve past question in my next video, and you're going to see how to apply all these definitions that I have given. Thank you for listening. See you in the next class. Enjoy.